If C is the length of the hypotenuse of a right-angled triangles whose other sides are of the length A and B, then by the theorem of Pythagoras, a squared plus b squared equals c squared. This fact can be derived by looking at the expression a plus b squared and interpreting that geometrically in two different ways. This is fun. We start by looking at a plus b squared. It is, of course, a plus b times a plus b, and that becomes a times a plus b times a plus b. A times a plus b is a squared plus ab. B times a plus b is ba plus b squared. So we have that a plus b squared is a squared plus ab plus ba plus b squared. ab is the same as ba, so this abbreviates to a squared plus 2 times ab plus b squared. So we have the formula a plus b squared is a squared plus 2 times ab plus b squared algebraically. Easy computation. Next, we interpret this geometrically. A plus b squared is the area of a square of side length a plus b. So we draw a square whose side length is a plus b, and the side consists of one segment which has length a and another one which has the length b. The area of such a square is, of course, a plus b squared. This square can be split into subdomains. First, we form the blue square and the red square. The blue square has the side length a, the red square has the side length b, so the area of the blue squared is a squared, the area of the red squared is b squared. Then the two yellow rectangles are left over. The sides of those rectangles are a and b, so the area of these two rectangles is a times b for both of them. And from this it follows that a plus b squared is a squared plus 2 times ab plus b squared geometrically. By splitting the square whose side length is a plus b and area a plus b squared into two squares and two rectangles, we obtain the geometric way to derive the formula a plus b squared is a squared plus 2 times ab plus b squared. We may take this a step further. Consider the right-angled triangle whose hypotenuse has the length c and whose shorter sides have the length a and b. Let T be the area of this right-angled triangle. Now we use this right-angled triangle, we split these two yellow squares that we had in the decomposition of this square of side length a plus b, and we split the two yellow rectangles into two right-angled triangles each by a diagonal. Now all these right-angled triangles, there are 4 of them now, have the same area T. And we have that a plus b squared is a squared plus b squared plus 4 times t. Now follows a magic move. We can rearrange the yellow right-angled triangles so that the right angles coincide with the right angles of this square. There are 4 triangles and 4 right angles in the square. So when we do this, we obtain this figure. Now the 4 right-angled triangles together with a one large square fill the whole initial square of side length a plus b. This square in the middle has the side length c, that is the length of the hypotenuse of these right-angled triangles. Therefore its area is also c squared. So we have that a plus b squared equals c squared plus 4 times t. We still have these 4 right-angled triangles. So we have 2 presentations for a plus b squared. So the left hands are the same, so the right hands must also be the same. So we get that c squared plus 4 times t equals a squared plus b squared plus 4 times t. 4 times t cancels out, and we get c squared equals a squared plus b squared. This is a formula of the theorem of Pythagoras. Pythagoras of Samos died approximately 500 to 490 before Christ. He invented the theorem which says that for a right-angled triangle whose hypotenusa has the length c and the shorter sides have the lengths a and b, a squared plus b squared equals c squared. This is a theorem that every high school student knows, or at least should know. This theorem of Pythagoras already appears in a clay tablet, in a Babylonian clay tablet that dates back to 1830 to 1531 before Christ. In these clay tablets, Babylonians explained how to compute an approximation of square root of 2. So it is clear that Babylonians knew a special case of the theorem of Pythagoras. They knew it over 1000 years before Pythagoras. Namely, they knew that the length of the diagonal of a square of side length 1 has the length square root of 2. Perhaps the theorem of Pythagoras should more rightly be called a formula of Babylonia.